Okay, it's coming up. Just 1 second. Okay, we are on live now. So yeah, I think we can start. Now we have Céline Combet from Renault. She will be talking about the dark matter modeling of astrophysical targets at different scales. And this is something like a preparatory lecture for the clumpy hands-on sessions in the afternoon. Okay, so I think you will find it particularly useful also for the hands-on session. Okay, Celine, so the floor is yours. Thank you so much for being here today with us. Yeah, you have until 2 p.m.
Okay, great. And thanks for inviting me. And hopefully next time we can all go to Madrid.
Yeah,
So hi, everyone. So my name is Celine, and as Miguel just mentioned, I will talk about dark matter modeling of astrophysical targets. This is something that has kept my collaborator and I busy for the last 10 years in sort of an on and off sequence. And basically, we've been working at developing this clumpy code that allows to have a lot of flexibility in this modeling. So the goal of this lecture is really twofold. I hope, to be able to show you the basics of dark matter halo modeling, and then we'll focus a bit more on the specific targets we want to look at. One thing I would like to get across as well is for you to understand and grasp the limitation and uncertainties linked to the dark matter modeling of this target. And hopefully you'll have all you need for this afternoon clumpy session that Moritz Hutten will be leading. The outline of this lecture is as follows. So we're going to do a quick reminder of structure formation, basic halo modeling. Then we'll dig deeper into the actual gamma ray signal from dark matter annihilation and decay we expect, and why knowing the dark matter distribution is so important in that context. And then we'll focus, as I said, on a few galactic targets and also on the extragalactic scale. So you should not hesitate to interrupt me at any stage. So I will try to monitor hand raised in the participant list. You can also maybe put question in the chat. And if I don't see your hand or anything, shout at me to make sure I'm aware that you have a question. Okay, so let us get started with a quick reminder about structure formation. So you did have earlier last week an entire lecture dedicated to this, so we're going to go quickly. And just here, I just want to remind you that structure in the universe form from the fluctuation of a primordial density field. The growth of structure depends on the underlying cosmology and on your cosmological parameters, and is basically a fight between expansion and gravity. From this, halos will form from the high density region. And today, the universe we're seeing, and this is a snapshot at z equals 0 from a dark matter only simulation of Benedict Dimmer, we have a universe that is highly structured with voids, filaments, and halos. And in particular, the largest halos are forming at the intersection of the filaments, and we are associating those to galaxy clusters today. So an important statistical information regarding the halos in the universe is the halo mass function. And it's the number density of halos as a function of mass and redshift. And on the right, you see how it behaves. So this is this number density per unit mass as a function of the mass for different redshift. So the first thing to notice is that I have much more low mass halos than high mass one. And the other thing is that if I'm looking at the galaxy cluster scale, 10 to the 15 solar masses, I have less halos of this mass at z equal 1 than today. And this is because of the hierarchical structure formation and the fact that it takes time to build and make large halos. So you will always have more massive halos. You'll have more today than in the past. So the overall description of this was first described by Preston Chester. There were some later analytical refinement, but today, generally, people come and adjust this halo mass function on numerical simulations, be them dark matter only or hydrodynamical simulation. And there will be tiny difference in the halo mass function that people will predict. Now zooming on, so we were at the very large scale, so now I'm zooming on the galaxy cluster scale, and the notion, again, because of the bottom-up structure formation, the smallest halo will first collapse and then merge into larger structure. And the picture we have today is of halos within halos within halos. And this is the Aquarius simulation, so it dates by, 2000, so it's a long time ago, now 12 years old, 12 years ago. Where you had a galactic Milky Way-like dark matter halo. And you see a smooth contribution of the dark matter density here, the sort of pinkish region, but you also have very high density clumps or subhalos. And if you go and zoom into those subhalos themselves, they have substructure within them. So really, this is a sort of Russian doll picture of halos in halos in halos. And in terms of mass range, we know that the largest halos we can have are galactic cluster type halos with 10 to the 15 solar masses. But the minimum mass will depend on the free streaming scale on your dark matter model. So this is more uncertain. And typically, people generally consider 10 to the minus 6 in most analyses as the minimum mass of dark matter halos you can form. Now, just a little word of caution, the minimum mass you get in a numerical simulation depends on the on the resolution of the simulation. So these two should not be mixed up. So here I'm really talking about the sort of theoretical minimum mass you can have for a halo. Okay, so last thing is that, so where are those halos? Well, there are some we can see because the most massive ones will have accumulated gas. They will have star formation will have been triggered, and these are what we see today as galaxies in galaxy clusters or dwarf solar galaxies. So some of them we know the location of, and we can directly point our telescope towards. However, again, from this picture, I have halos going potentially all the way down to the 10 to the minus 6 solar masses. They won't have formed stars, and so there are plenty of low mass halos that we are not seeing. The last thing here is that I've added a little spiral galaxy in the middle of this Milky Way type halo. And this is just to highlight the fact that the galaxy we see and the stars, the extension of this is extremely small compared to the size of the galactic halo. So our galaxy is split into 20 kiloparsecs or something, where the halo would be about, I don't know, 300 kiloparsecs. Okay, so now let's move to sort of the basics of dark matter halo modeling. So first of all, before going to the spherical K approximation, I want to remind you that halos in the simulation are generally found triaxial and preferentially prolate. So it means there's really three axes, but the first simplification we're going to start making is assuming everything is spherically symmetric. And then you can go and measure the density profile as a function of the distance of the center. And there are two main parameterizations that are used, that are the NFW profile or the anasto profile. So the NFW profile has only two free parameters, ρs and rs. The anasto profile has rho minus 2, r minus 2, and a slope alpha. And r minus 2 is simply the radius at which the logarithmic slope of the profile equals minus 2. So on the right, you have an NFW profile, which has a slope that tends to minus 1 in the inner region, minus 2 in the outer region, and it goes through a slope equal to minus 2 at r equal rs. And the anasto profile with the slope alpha has a continuously changing slope, logarithmic slope, and I'm calling r minus 2 the location where the slope is minus 2. Okay, so basically you have two or three free parameters. Now looking at numerical simulation, and this is recent work from Wang et al., what they found is that the NFW or the anasto profile with this value for the slope are very good representation of the density profile in halos over a very wide range of masses. So they are using a technique of zooming simulation, and they have a level 0, which corresponds to galaxy cluster scale. You see here 10 to the 14 in light blue. And they are able to resolve halo all the way to 10 to the minus 6 solar masses. And here they're plotting the best fit, they're plotting the logarithmic slope for all the level of the simulation. And you see below on the bottom panel, the residual to the best fit NFW or an astro profile. And over a wide range of radii, these do a pretty good job at representing the density profile. And you see you have like a 10% scatter here. And especially an astro with this value of the slope is doing pretty well. So if I'm only concerned with dark matter only simulation, everything seems pretty consistent, and it seems that I'm able to model my halos, whatever the mass range, using those parametrization. Now this is just showing you an astro with an alpha equal 0.16, and I've normalized them both to their scale radius. So this is just showing that they indeed look pretty similar. So now we have a density profile very well, and I can in principle integrate that density up to infinity, and I might get an infinite mass, and this can diverge. So we need to know also where galactic halos end. So this brings me to the notion of spherical over density, mass, and radius definition. So what is generally done is that we're going to say that a halo has a mass m delta when this allows us to define the radius r delta within which the average density of that halo is delta time a background density. Okay, so I just have the volume of the sphere, r delta, and I have an average density that is delta time some background value. For the background value, there's two options in the literature. People do use the critical density of the universe or the mean density of the universe, which is just the critical times omega m. So you see from this, you're gonna find in the literature definition called M200C. So that's gonna be the mass over density mass with delta equal 200 with respect to the critical density. But you can have M200M, where this time people have used the mean density of the universe, or have another value for delta, M500C, and so on. So just a word of caution, you need to be careful about the mass definition that you see in the literature. Mass is not just a mass, you need to be aware of the mass definition. So now I have a quick question for you. Given this definition, and I've just suggest you use the raise hand button on Zoom. So given this definition, what radius is the largest? Is that R200 or R500? So please raise your hand who thinks R200 is largest than R500. I'm going to give you a second just to think about it. So we're talking about the radius within which the mean density of the halo is either 200 times or 500 times larger. So I have a few hands being raised. So R200 larger than 5R100. I think I have two, only two people, three, a bit more, okay. I'm waiting an extra 10 seconds. Okay. Okay, great. So it looks like we're almost all in agreement. So indeed, R200 is larger than R500. The density is a decreasing function. So to have a mean density 500 times larger, you need to stop integrating to get your average density at a lower radii. Okay, this is it. So now in the literature, you will often see 200 has been used at the halo size. And just to give you an order of magnitude, for the smallest halos I can think of, 10 to the minus 6 solar masses, typically 1 Earth mass, the size of the halo will be around 60,000 AU. So that's the distance to the Oort cloud, that's the distance of our extended solar system. So these are very diffuse thing, okay? 10 to the minus 6 solar masses in the size of the solar system. Now, if I go to the extreme other end, 10 to the 15 solar masses is a 2 megaparsec, so that's your galaxy cluster typical size. Another important thing is the concentration parameters, which is defined at the radius of r delta over the radius at which this slope was equal to -2. And for an FW, this is just the scale radius rs. So if I have a profile that's at two parameter rho -2 and r -2, I can completely and equivalently determine it if I only have m delta and c delta. Because if I have m delta, I can compute r delta. And if I know the concentration, then this gives me the scale radius. Now, m delta is also the integration of the mass within from 0 to r delta of the density. And so this allows me to compute the normalization. So in general, to characterize a dark matter halo, you can provide ρs and rs, or a mass and a concentration, and you're able to normalize it and have the actual values. So here you have the density as a function of radius for a 10 to the 15 solar mass halo, where I've increased the concentration. And what this does is that this is moving inward the scale radius. This is an NFW profile. So those vertical dotted line are RS. And I have a higher density for more concentrated halos than I have for less concentrated one. So you probably had got that from the word concentration, but this is just illustrating what it is. But then, can I take anything for a concentration? Answer is no. There is a relation between mass and concentration. And here, this is from work from a few years ago by Miguel, where you have the mass of the halo and a function of their concentration, and with result of various numerical simulation. And what you're seeing is the low mass halos are more concentrated than high mass one. And there is also a redshift dependence that roughly goes as 1 plus z, where the halos are less concentrated at higher redshift. So what I've done here is not really acceptable, because there is in principle a relation between mass and concentration. Okay, so this is the situation for general from dark matter only simulation. But we heard a lot about, and we hear a lot about cusp versus core. So dark matter only tell you dark matter halos are cuspy. The inner slope is steep. It's equal to 1 for an NFW profile. There is also another process by which the presence of a condensation of baryon or central black hole can increase the slope and make the halo actually cuspier through some adiabatic contraction. So this is sort of an effect giving you a steeper profile. But if you go and observe and derive the profile from galaxies, dwarf galaxies, some results suggest that the density can be cored with the inner slope tending to 0. So this is the cusp versus core problem. And actually, there's various possible solutions for this. One of them is that baryonic feedback is responsible for producing core. And I think this was briefly mentioned by Annalisa Pilipic during our hydrodynamical simulation lecture last week. This is a density profile in a hydro simulation where they have increased the amount of star and stellar feedback. And you can see that if I have little star and little feedback, the dark matter and the hydro profile agree, but I increase the effect of baryons, the profiles tend to become cored for the hydro simulation. So that's one way to do it. Other people are also using or thinking of other type of dark matter models, such as self-interacting dark matter, that can solve this. But for our purpose today, which is going to be to predict the dark matter indirect detection signal, all we need is some parameterization to capture this. So you can all use the astro profile and maybe use an alpha, a different alpha that allows you to have something more cored, or a more general parameterization, such as the Dow parameterization, which reduces to an FW for alpha, beta, gamma equal 131. But gamma is the inner slope, I have beta the outer slope, and I have some transition controlled by the alpha parameter. So NFW is only a 2 free parameter profile. This becomes sort of a 5 free parameter profile, but it allows you really to capture any shapes you want. Okay, so very good. So this sort of concludes the generic dark matter halo modeling part. Are there any questions regarding this? Hopefully this was clear. I'm going to wait 5 seconds just in case. Okay, good. So now let's move on to a bit deeper into what's our concern today, which is predicting the sort of exotic gamma ray signal from dark matter annihilation or decay. And we're going to start with a toyish model. We're going to consider a volume V in which there are n dark matter particles. If the dark matter particle is its own anti-particle, then I have n particle like this. If it's not, I'm going to split the number of particles between the dark matter particle and its anti-particle, and I have n/2 for each. So now I'm first considering a single pair with a projectile and a target, and the annihilation or the reaction cross-section is going to be sigma, and they have a relative velocity v. So the sort of probability of interaction in this volume v is given by the test volume of the interaction, sigma v dt, divided by the volume. Now, I'm going to move and express this, the total annihilation rate, so per second, in the entire volume V. So what I need to do is first divide this by dt to have an actual rate. And I need to sum over all the pairs I have available, projectile target pairs available in my volume V. And here, this is when you need to be careful on the type of dark matter you're considering. If the dark matter is its own anti-particle, chi equal chi bar, then I have n projectile, but they can interact only with n-1 targets, and I need to divide this by 2 to avoid double counting. And for a large number of n, this is n²/2. However, if the dark matter is not its own anti-particle, then I have n/2 targets that can interact with n/2 projectiles, so this is n²/4. So here we see we have a tiny difference depending on the model of dark matter we're considering. Now, we're going to take this annihilation rate and compute it per unit of volume. So I'm dividing again by a volume. So I'm going to have a v² here. n²/v² is going to be the numerical density of particle in here. And the numerical density is the mass density divided by the mass of the particle. So when I do this, my rate per unit of volume becomes this expression where now I have the mass of the candidate and I have delta equal 2 or 4 depending on the type of dark matter I'm considering. So very well, so now we have a number, a rate of annihilation in this volume, per unit volume. Now to actually find the rate, the photon emission rate of this source, I need to multiply this number of annihilation by the number of photons per unit energy, that I am producing for each annihilation. So this is your photon spectrum, and this is the total source photon emission rate. Okay. Is this okay for everyone at this stage? I don't see any hand raised or anything, so let's move on. So this was the source. Now I'm located at in distant L from this source, and I have a detector with a surface area A. So what is the photon rate I am going to receive at my detector? So I need to take the rate emitted at the source. The source is emitting in all directions, so I have a 4 pi L squared, and I multiply by the reception area of my detector A. So this is all really well, and we have a nice toy model, but now the actual situation looks like this. I have a CTA or Fermi or whatever, And I'm looking across the galaxy all the way along a given line of sight. So the differential flux I will receive, I need to integrate this over the entire observation volume, not my only little volume V. So this flux is going to be the rate divided by the surface area, because I want a flux per square centimeter or something. And I need to integrate this over the entire volume. If I introduce the spherical volume element dV, so L is along the line of sight here, I'm going to have an angle alpha, which will control the opening angle of the cone that I'm observing, and beta is just the angle that goes from 0 from 2 pi to define the observational cone. So this is the elemental volume element. The L square are simplifying between the one I had here at the top and at the bottom. And at the end of the day, the flux I receive is expressed like this. You have annihilation cross-section, you have the mass of the particle, you have the spectrum of the photon you're emitting per each annihilation. And you are multiplying this by the integration along the full line of sight of the dark matter density square. So here, I have assumed that sigma V is constant, so it can be factored out. But that's not necessarily the case, and I think maybe Francesca Calore tomorrow will mention some model and some limits obtained where you do not make that assumption. And if you don't make this assumption, this cannot be expressed as simply as this. So now I just want to say a quick word about decay. If I have decaying dark matter, this is a single particle process. So you just have to change this delta and put it equal to 1. The sigma V is becoming the lifetime, the lifetime of your decaying particle. And because this is again a single particle process, rho and m squared simply become density and m. Okay, so for decay things are a bit simpler. So at the end of the day, to just recap at this stage, the flux I'm measuring at Earth for a given energy in a given direction k over a given opening angle alpha int is expressed as a product of a particle physics term that depends on your particle physics candidate, the mass of the particle, its thermally average annihilation cross-section. Here, the spectrum, I've changed a little bit how it's written. Here we are summing up of all the channels that at the end will produce gamma rays, okay? So this is a sum of all the channels with the branching ratios for each channel. And this is multiplied by the so-called astrophysical J factor. That is simply the integration of the dark matter density square over the volume. So once you have this, assuming you're able to predict your J factor, you can go ahead and place limits or contours, depending whether you have an excess or not in your gamma ray data, in the plane of the cross-section, the annihilation cross-section mass of your candidate, and compare this to the thermal relic cross-section that you expect from the early universe. So to actually go from there to sort of these exclusion plots or contours, you have to do some very complicated data analysis, and you had the lecture from Christopher Weniger pointing, for example, for the galactic center, it's still not clear, people are still not agreeing whether it's pure, there is an excess, and it could be an exotic component, or if this is millisecond pulsar. So there's a lot of work to actually get to those limits. But today, and in the rest of this lecture, I am going to focus solely on the J factor, because if you want to place robust limit here at the bottom right, you need to have robust determination of the J factor, which means you need to have robust determination of the density in your targets. Okay. Oh, and just a little thing before moving on. This 4 pi, you've seen it, I've put it in the particle physics sometime, and especially I think in earlier paper, sometimes people had it in the J factor definition, so it is a source of confusion. So if you try to reproduce some results from some paper, make sure you've checked where the 4 pi was located. Okay, so very good. So now let's move to some general consideration on the computation of this J factor. So here's the global picture again. I need to integrate over the line of sight. And if I don't know anything in particular, rho is a complicated function, because here it would mean I need to integrate the density square of each substructure I'm seeing of the smooth, and maybe I also have a target, which is its own dark matter halo that itself has some substructure. So doing that computation is actually not straightforward, and rho is a complicated function. And also, wherever we look at, we're also crossing the dark matter halo of the Milky Way. We're never simply looking at a target, okay? So let's go and see what ingredients we need to predict the J factor, and what are the effects of those substructure on the J factor. Okay, so the first little toy model, we're gonna, so I removed the galaxy. Let's forget about the Milky Way. I have a halo that is fully encompassed in my line of sight, and the distance from the observer is really large compared to the size of the halo. So what I want you to do or think of quickly is, how do I compute the J factor? How does this get simplified with those assumptions? And I'm going to wait, I don't know, maybe 30 seconds or something, if someone want to tell us what you think would happen. This would make this should become much simpler. So is anyone finding a solution to that question they want to share? Okay. Oh, I see something in the chat, sorry. Oops, I did not see the chat. There is a question there. These mass relations are the same for annihilation or decay. Claudio, sorry, I'm just seeing your question now. You were referring to the demonstration we had earlier? Okay, well, maybe Claudio is not, cannot speak yet, but yeah, so if you're referring to the demonstration, you can really go through all the same steps with decay and not annihilation. So you're keeping everything, you're just switching at the end, mass square by mass, rho square by rho, everything else remains the same. Okay, and I think someone was talking just before I saw the question from Claudio.
Yeah, I was just gonna guess. I wasn't actually sure of the exact way to do this, but I was thinking that surely your angle dependence wouldn't be important anymore, so that would be negligible. So I'm guessing that you just left with the integral over the line of sight with the density, you know, just over that distance, and then you don't take into account the alpha or the beta, but I'm not sure exactly.
Yeah, no, I think you're getting to the right solution here. So what you're doing in that case, and I think so, we're still going to integrate over the volume of the halo, but it's zero. Basically, the density is zero everywhere, but over the volume of the halo. So if I multiply and divide by L square here, my expression, if I multiply by L square, I have the volume element in spherical coordinate appearing again. And this just becomes the integration over the volume of the halo of the density squared. But I've also divided by L squared, but I can take this one and put it out of the integral because I'm so far away. This just become, okay, now I'm calling it D. This just become a scaling with the distance squared. So in your point-like approximation, your jet factor is just what I'm going to call the halo luminosity, density squared of this thing integrated over its volume. I don't really care about integrating over the distance here. And I'm only dividing by density squared. So if I do a very roughly, I look at what this is. This is the mass squared divided by the density square, and I have a volume here. So this is telling you in this sort of very naive toy model that the best targets are massive, they are dense because I have a m over v here, and they need to be close by. Okay, so now let's move away from this approximation and have an extended source, and it has a smooth dark matter density here. So the jet factor, I don't have a choice now. I cannot do any simplification, and I need to integrate over this volume, whatever it is. Now let's move one step further, and let's include substructure. So here I'm taking a fraction of the mass of the host halo, and I've turned that into some substructure, so that the total dark matter profile, I'm writing this as a smooth dark matter profile plus sort of an average contribution from the substructure, which depends on basically the radial dependence of the substructure. And here, if I compute the jet factor here, formally what I need to do is I need to integrate along the line of sight the smooth, and I need to sum over all the clumps I have in my line of sight and put this squared. So what is this going to do? And again, I'm going to give you maybe a minute to think about this 1D toy model, where I have a host halo, in gray, where I have a smooth and no substructure. And I am turning all this mass, so I'm going to use a fraction here equal to 1, into substructures that have a density twice as large as the original host halo, but of course a smaller extension because I need to conserve mass. So if I do this, what's going to be the jet factor in this toy model? And again, I'm just going to wait a little bit for you to think about this. All right, so let's go again through a show of hands. Who thinks it won't make any difference? The jet factor in configuration, in the pink configuration or the gray configuration, is going to stay the same. Okay, no hands. I like that. Who thinks I'm going to have more signal with the substructure than without substructures? Okay, I see a few hands starting. I see one hand. 2, okay. Anyone else? Yeah, this is starting to arrive. Okay. Okay, this looks like we have at least six or so people thinking that and more arriving. Okay, substructure will give more signal. Lower your hand. Is anyone else thinking that maybe that's not the case and that I'll have less signal with substructure? No. Okay. So indeed, I'm doing my little toy model here. So I'm integrating in one case, I'm integrating rho squared. On the other case, I'm integrating on the sum of those two substructure 2 times rho squared over a smaller radial range. And at the end, I have a factor 2 difference, and I will have more signal if I have substructure than I have the same amount of mass without substructure. So what about decay now? Our substructure going to make a difference for decay? Hands up if you don't think it's going to do anything. So if substructure have no influence on decay, please raise your hand. Okay, Lorenzo. Okay, maybe there was too many negative statement in this sentence. So if I have decay, I'm only integrating the density here. Remember, I don't have the square. So I'm only basically integrating the mass. So for the decay, it doesn't matter how you've spread out your mass in substructure or not. At the end of the day, your D factor is not going to change. So no boost from substructure when you have decay. Substructure are only relevant if you're dealing with annihilation. Very good. So now we know substructure should, in principle, increase my signal, but it doesn't help me. The toy model really doesn't help me to get closer to the solution. So I'm going to take my expression here at the top, and I'm going to expand in three terms. You have the rho smooth squared, you have the cross product between the smooth and the clumps, and you have the squared over all the clumps. And from this, I can't really do anything because I have no idea of the actual realization of the distribution of the substructure in the halo I'm considering. So the way to get across this is to move to the continuous limit and use distribution function. So here, I'm going to say that the number of halos I have in a mass interval dm, in a volume dv, and in a concentration range dc is equal to the total number of halo times distribution. Distribution with the spatial distribution, the mass distribution, and the concentration distribution. Remember that if I have mass and concentration, you remember from the first part of the lecture, your dark matter halo profile is fully determined. So when I'm splitting this in three parts, I am assuming that I have no correlation between the spatial distribution and the mass and concentration one. And we will see later that this does not necessarily hold, but for the time being, this is what we're going to do. And I can go again into my favorite numerical simulation and have a look at what those distributions look like. So this is, again, the Aquarius simulation from Springle. And this is the spatial distribution, the radial distribution of substructure as a function of the distance in various mass range. And as you see, that it is really relatively well modeled by the dotted line here is in an astro profile. So from a purely parametric point of view, I can use an anasto profile to model the distribution of substructure in the host halo. You can also look at the mass distribution, and this roughly goes as function of the mass. It's a power law with an index roughly equal to 2, 1.1. So I have more low mass halos than I have more low mass subhalos, than I have high mass subhalos. And so this gives me the mass distribution. And I also need a concentration. Oh yeah, I had this. So we're not going to do this exercise here, but a quick question for you, maybe to work out later. If a simulation tells me there's about 100 subhalos between 10 to the 8 and 10 to the 10 solar mass halo, how does that make, how many subhalos do I expect from a Milky Way-like galaxy host halo if the minimum mass is 10 to the minus 6 solar masses? So this is just to get an order of magnitude of what we're dealing with, but you can do this later. So I was saying earlier, we also need a mass concentration relation. This is the picture I showed you earlier, and there is a mean mass concentration relation here in the solid line, but the gray band here represents the scatter. It means that for the same mass, not whole halos are going to have the same concentration, and the dispersion of this, the distribution of the scatter is generally well modeled with a log normal distribution expressed this way. So now I have ingredients that give me the full statistical property of my subhalo population. So this means that when I come back here, I can go ahead and express those discrete sums using the distribution we just discussed. So you can work this out for yourself, but here we're just going to move directly to the answer. For the cross product, this becomes simply the integration of the smooth time, the spatial distribution of the subhalos times the total mass in the subhalos. So I have a host halo. I took a fraction f of mass that I put under the form of substructures. And so my average subhalo contribution is just this. And now, more interestingly, the last term is the contribution from the sum over all my clumps. And this becomes this complicated integral where I have here the single halo luminosity. This is the one we saw in the point-like approximation. So simply the integration of the density squared of the subhalo over the volume. And it needs to be integrated over the mass concentration, the concentration distribution, the mass distribution, and the spatial distribution. So this becomes a little bit involved, but with these three expressions, you are able to compute what is the total J factor for a halo given a population of subhalos within that host halo. Okay, is this, did I lose anyone or everyone, or is this roughly clear? So again, use the chat if you have questions, raise your hand. Do not hesitate to interrupt me. Okay, so now I can go. So we with our toy model earlier, we saw that substructure should boost the signal. And now that I have a description for all those terms, I can define the boost as the ratio of the total J factor when I have substructure divided by the case where I did not have any substructure involved. And here's the figure on the right is the boost as a function of the halo mass, the host halo mass, sorry. I should be more specific. So the boost, as we just saw, depends on a lot of parameters and choices, because at the end, these are user-defined choices. You need a spatial distribution, mass concentration relation, and a distribution for the concentration, a density profile for the halo, a given mass range. So all these matter. So here there is some configuration when 20% of the mass of the host halo was turned into subhalos. The boost is calculated down to a minimum mass to 10 to the minus 6. In blue and black, I have two choices for the mass concentration relation. And the various line style are for various choice for the slope of the mass function. So simulation gives you 1.9 typically, and we went and tried something a little bit steeper with 2.0. And as you can see that the boost depends on the host halo mass. So the largest halo, the most massive halo, can have boost up to a factor of 10 or 50, let's say. Whereas low mass halo, the boost disappears when you go to lower masses. The other thing I want you to think about and understand is that the value of the boost also depends on the geometry. Here I have the differential J factor per steradian. It's divided by the solid angle, so it's just the integration along the line of sight without the integration of the on the angle. And this is looking from the center of an external halo towards the outskirts. So here in green, I have a line of sight that goes right through the center. And right through the center, the most contribution I have to the total J factor, which is the solid black curve, comes from the smooth. The substructure have very little role to play in the inner region, and the smooth completely dominates the signal. However, if I'm looking a bit outside the central region, this time the smooth has decreased, but the substructure are starting to kick in, and so I will expect a boost from the substructure here. Similarly, if I'm using a large integration angle, the boost from structure will play a role. But if I only look in the center, there's no really need to include substructure in your modeling. Okay, and the last bit, I'm going to go very quickly here. So far, we had one level of substructure, but from the hierarchical structure formation, I do expect to have halos in halos in halos, so a multi-level substructure scenario. So you can show, and I will leave that to you as well, but you can, if you have n level of substructure, you can show that the luminosity, I'm talking about the overall luminosity of this halo here, with n level of substructure, it can be recursively computed this way, where you at some point need the luminosity of your subhalos at level n-1. So it doesn't matter, you can work this out, it's a bit painful, but we have a way to go through multi-level substructure boost. And if you do this is similarly as before. I have the mass of the host halo on the x-axis, and here I'm looking at the relative difference between adding 2 levels of substructure compared to 1, 3 compared to 2, 4 compared to 3. So indeed, if you add a second level, you can see that for the most massive halo, you have at most 30% increase in your J factor. So you gain a little bit, but this quickly converges. So actually, there's no need to really go beyond level 1. And even, okay, you can go to level 2 if you want to, and you will gain a little bit, but really keeping with 1 level of substructure for the calculation is generally enough, especially because then it becomes really computationally expensive to actually do this calculation accurately. Okay, so a quick recap for the first part of this lecture. My J factor is defined as the equation above, and if I go to decay, just to remind you that I simply have the square that is disappearing. To do anything with indirect detection, I need robust determination of those J factors. And to actually model the dark matter distribution, we will assume spherical symmetry. That's super standard, even though we know halos are triaxial. And we will use a smooth component and possibly a subhalo population that may come and boost the signal. But now, you've seen so far, I've relied in what I told you, I relied a lot on results from numerical simulation, either dark matter only or hydro simulation. But actually, there is information to be gained when you start studying specific objects. There is information to be gained at looking at observation, astrophysical observation in those objects. And this is what we were going to see in the second half of the lecture. So, I see a question. Yes, is there any specific criteria on apparent angular size for when a halo can be considered point-like as opposed to extended? How would one determine which case to use? Okay, that's a good point. So if you have a host halo, so basically it depends on what your instrument angular resolution is and the angle over which you want to integrate. You can always integrate the signal over a very large angle, and then everything is point-like, right? So that's not, so really it's a combination of what your experimental setup is. And for example, a ground-based Cherenkov detector would have a much better angular resolution than, say, Fermi. So generally, Fermi will integrate on 0.5 degrees, something like this. Whereas if you look at a result from ground-based telescope, they will integrate the signal on smaller regions. And then if you have a rough estimation of the mass of your halo or of its size and its distance, then you can see roughly in what situation you are. Obviously, even a very small halo located really close to you can be extended depending on your opening angle. So it really depends on how large you want to integrate your signal. Okay, thanks. So I just realized I did not take a glass of water with me. So because we're halfway through, I'm going to suggest we take a 1 minute, 2 minute break. You can think of other question and I'll be right back because I need a little bit of water. So sorry about this. Okay, so if there are no other question on this first part, let's move on to looking at more specifically what targets we have and how we constrain the dark matter in those targets. And why can't I change slide? Okay, so this is something you might have heard already from lectures or previous presenters in terms of where do we look at, but let's go again briefly to what makes a good target. So roughly, it needs to be massive and dense, and I'm going to add to this because we do need robust estimation of the density. So the more robust the estimation you can do of the density, the better it is. If it can be located close to us, because of the d squared quantity here, it's all the better. It has to have as little, astrophysical gamma ray background. So from Michele's lecture last week, I think you heard about all the possible process that can generate gamma rays from astrophysical processes. I think Christopher also mentioned, for example, for the galactic center, there is controversy whether you can have this excess is only from astrophysical origin or if it's exotic. So basically, if you go to a place that is as clean as possible and has as little background as possible, all those discussion becomes more simple. And optionally, it is visible at other wavelengths because then you can get some more information about it and you know where to point your instrument. So in the rest of the lecture, we're going to go briefly to what's happening at the galactic center, because it's obviously a nice place to look at because it's quite close and potentially dense. We're going to talk about the dwarf-throttled galaxies. So these are satellite galaxies that are orbiting in our own Milky Way halo. Okay, they would correspond to the most massive subhalos of the Milky Way halo. We're going to discuss dark clumps. So in their case, they haven't formed stars, so we don't know where they are, but from statistical consideration, it's still possible to use them to place some limits on the dark matter properties. And a bit further away from us, we have our neighbors galaxy clusters. So they are very dense, but they're also further away. So the d square is going to be a bit more of a problem. But if I'm looking only in terms of density here on the bottom left, I took an NFW profile for everyone. I have different masses going from the lowest possible clump to galaxy clusters. And you remember that the mass concentration increases with decreasing mass. So I'm using more concentration, higher concentration for the subhalos than I'm using for the galaxy clusters. But despite this, the hierarchy is still respected. It means that I'm still going to have denser region in a galaxy cluster than I have at a galactic scale halo, than I have at a dwarf-throttled galaxy scale, or that I have for a dark halo. So it would really take huge concentration to get this hierarchy to cross over. So those lines, this ordering of line is generally respected, and the galaxy clusters are the densest place in the universe in terms of dark matter. So we're going to go through the specific for each target, but a little bit of a disclaimer. In the recent years, people have started also looking at dwarf irregular galaxies. So these are galaxies in terms of mass that are in between the dwarf galaxy we're going to study in a minute and Milky Way type halos. And some of them are part of our local group. So they have typical distance of the megaparsec scale, say, so not so far. So they could be interesting for indirect detection. The only thing is that these are galaxies that are forming stars. They have active star forming regions, so there might be some gamma ray background. So these I'm not going to discuss, but in terms of in this plane where I have the level of background and possible J factor value. So this is where, sorry, I should have mentioned these axes before. This is where our different targets lie. I'm going to put them somewhere in the middle here between the dwarfs and the clusters, but I'm not going to address those. Okay, let's get started with dark matter modeling at the galactic scale, starting off with the galactic center region. So again, you've heard from earlier in the week that galaxy center it's very interesting. There is the success, there's lots going on, but actually there is a lot going on with respect to understanding the background and the data analysis. But in terms of the actual dark matter modeling you need to put in there to get the J factor, things have stayed roughly the same and are not necessarily very, very complicated. So, okay, we should have a large J factor because the Milky Way is relatively massive and we are only 8.5 kiloparsecs from it. So this D square is working in our favor here for the galactic center. But it's complex because of all the astrophysical processes and you need some estimation of the dark matter profile. So how to do this? You could really go to your favorite numerical simulation, take a Milky Way-like halo, NFW profile, take the properties from there and say, okay, this is my model. But in practice, we can do a little bit better. And okay, this is not something I've worked on, so I'm going to stay quite in an overview mode here. But people are adjusting multi-component mass model to the galactic rotation curve. So here we're really back to the thing that allow people to infer the presence of dark matter. You have rotation curves of galaxies, and you see that the circular velocities of the star is not what they should be if there was only visible matter. But so this is kind of an evolved version of that, where in terms of component, people consider a dark matter halo, generally spherically symmetric, but you need a stellar disk, you need gas, you need a stellar bulge. All these could have relatively complex morphologies and could be inferred from observation. And you have a compilation of kinematic data to produce a velocity rotation curve as the function of the distance from the center of the galaxy. And here is just an example from this paper where you have the contribution of the three baryonic mass component and the dark matter you need to add to explain the velocity rotation curve. So I'm not going to say more about this, except that that's not the only approach. There are other things that can be done at the galactic scale, always looking at kinematic traces. But generally people will, using this, determine the local dark matter density. So what's the density at the sun, basically. And sometime they will also let the dark matter profile parameter be free and attempt to fit those. But in any case, the thing to remember that the inner slope is never really well constrained. So for us, this is important. So what we do generally then, that you're going to find some parameterization, a combination of what you find in the simulation or in the literature. So for example, what has been often used to describe the galactic halo is take an NFW profile with the scale radius roughly of 20 kiloparsec. Same for an astro profile, but with this kind of slope. And then if you have RS from somewhere, then you can use the measurement of the local dark matter density to scale your dark matter profile and get the normalization ρS. Alternatively, you can also take the measurement of the local dark matter density and try to see if you can find an enclosed mass within a given radius, and that will also allow you to normalize your profile. But if you look at the analysis that were done either in Hess or Fermi-Lat, for example, for the galactic center, because the inner slope is not something that is really well constrained, generally you also want to play a bit with the gamma, your inner slope, to try to cover the possible range of values. So last thing regarding the galactic center, should I worry about substructure when I look at the galactic center? Answer is no. This is the same plot as before. So the J factor divided by the solid angle, sorry. It peaks in the inner region and goes down as you move away from the galactic center. Here I'm only looking up to a region within 10 degrees of the galactic center, because this is a galactic center analysis. Putting 20% of substructure, you can see that the level here are really small compared to the smooth, so that really you don't want to worry about substructure for this particular type of work with the galactic center. Okay, so it's a bit strange, because despite the fact that this is probably one of the most interesting places to look at, and that there's so much going on in trying to understand what's happening at the galactic center, in terms of dark matter modeling, we're still not, the model is quite straightforward. I'm going to spend a little bit more time now on the dwarf spheroidal galaxies. So, oops, why can't I switch slide? Okay. So the dwarf spheroidal galaxies are a population of galaxies that are orbiting the Milky Way. So they are located within our dark matter halo. They're constituted, they have all population of stars. There's no active star formation, so we don't expect any background, gamma ray background. So in that sense, they're a very clean environment to look at. The other good thing is that they're really close to us, and the closest is about 20 kiloparsecs, which made the 1/d square factor quite interesting. And up until 2005, we knew 8 of them. And these are what I'm going to call afterward the classical dwarf spheroidal galaxies. And they were found in photometric photographic plates. But in 2005, the Sloan Digital Sky Survey came online, which was able to detect much fainter objects in an automated fashion. And all of a sudden, the number of dwarfs we knew about exploded to get about 25 known dwarfs up to the early 2010, something like that. But now we have a new generation of a photometric survey that have come along. There's a dark energy survey, there's Gaia, there's HSC, there's pan-stars, and in all of them, since then, again, the number of potential satellite galaxy in our own Milky Way halo has exploded, and now we are at about 60. So there's 2 things. Before we move to the specific of indirect detection, I also want to say that this is related to the so-called missing satellite problem that you probably heard about earlier in the week. And actually having a good census of the satellite galaxies is very important because, you know, say, oh, there's a missing satellite problem, maybe my simulation are not right, and I need baryons, I need something to sort of reduce the number that I'm seeing. But on the observational side, we're still also in the process counting all those satellites. But that's not the topic today. They are interesting because they are heavily dark matter dominated systems. And you can see here, there's open and solid point, because to actually confirm that something is an actual galaxy and not just a star cluster, you need spectroscopic confirmation. So in terms of observable, what you have are photometry. So this is the Fornax dwarf. You just see a little enhancement of stars in a given direction in the sky. And if you have spectroscopy, you can go and measure the spectrum from individual stars in this object, and this will give you information about the velocity along the line of sight. And if you have this, you're able to measure a velocity dispersion, and the virial theorem that relates the velocity dispersion to the mass of the system, the virial theorem relates the two, and you can compute the so-called mass to light ratio this way. And if the mass to light ratio is high, it's most likely that you have a dwarf. If it's low, it's probably not dark matter dominated, and you're more dealing with a cluster. And here on the right, you have, so MV is not the mass here, it's the magnitude. So this is luminosity on the x-axis. This is the mass to light ratio for a few of those objects. And you clearly see two populations. The ones that have low mass to light ratio are just globular clusters, no dark matter. However, the dwarf galaxy sits higher, and for them to have the velocity dispersion we measure in them, we need to have more mass than what we're able to see. So at first level, you could try to find velocity dispersion for one of those galaxies, use the virial theorem to compute the mass, then maybe say, okay, I'm going to take an NFW profile, find some concentration, use some concentration and to scale your density profile and be done. But that's really not what you want to do, because we have much better way to constrain the dark matter profile in those objects than this sort of back on the envelope approach. So coming back to my observable, from the light, the photometry, you can measure the projected light profile as a function of the projected distance from the center of the object. From the spectroscopy, you can get the velocity dispersion profile each time as a function of the projected distance. So for Fornax, which is the one I showed you, this is what the light profile looks like. And this is the velocity dispersion profile. Now, there is one thing that relates the two, which is called the Jeans analysis. So I am not entering into the detail or showing you how this is derived. You can have a look at the Binet and Tremaine Galactic Dynamics book where this is done. Basically, you start with a collisionless Boltzmann equation. You integrate over the various moments of the velocity, and then you can combine this to get to the Jeans equation. And the Jeans equation relates the enclosed mass at a given radius to the actual kinematics that you're able to observe. So here, nu is the 3D stellar density, so the number of stars per volume. So it's in 3D. VR is the velocity dispersion, the radial velocity dispersion. I'm not going to enter into the detail of this anisotropic beta here, but the point is that if you give yourself some parameterization from the dark matter profile, NFW, anasto, whatever, you have parameters you want to fit, ρs, rs, and some shape, some slopes. Then the enclosed mass is completely determined from the parameterization you decided, you took. So you have your free parameters here. You can solve this equation then for the product of the 3D density, stellar density times the velocity dispersion, VR. And the last step, this is in 3D, but our observable are projected on the sky. So you need to project this and be able to compare to the actual observable you have for your object. So here, the take-home message is that given this observable, we're able to directly fit the parameters of the profile on this. So this is very interesting because here I have no assumption. I'm not making an assumption of a mass concentration relation from the simulation. I'm just using the data to directly go and normalize the profile. So there are some assumptions there. This does not come for free. You see spherical symmetry, dynamical equilibrium, no rotation. This can be limitations. In a parametric approach, you have potentially a lot of parameters because yes, you have the parameters of your dark matter profile, but you also need to some parametric form for the light profile. The one I swept under the rug here, the anisotropy. You also have potentially complex parametrization that depends on the radius. And finally, you want to put all this, say, in a Bayesian inference framework. You can make the choice of working with bin data or n-bin data. All those parameters need to have priors. You can make them more or less informative. So you're going to have different choices here as someone who is analyzing this data. And these different choices will yield to different results. So it's important to be aware of those limitations. And here I just want to show you that for the for 4 of the classical dwarf, the x-axis, is the distance from the center in kiloparsecs. Basically, these data does not allow us to actually fit the inner slope. You can see you get the same type of fit quality, whether you have, say, an NFW profile with gamma equal 1 or a core profile with gamma equal 0. So unfortunately, this is not really constraining the inner slope, but it helps nonetheless to, once you have an MCMC and with a change, you can propagate all these to your J factors and compute the J factor for all the dwarfs you have available. Here you have the result for all the dwarfs we had at the time, 5 years ago, and results from a few authors. The detail do not matter. All I want to get across here is that if you look at the most promising object here on the right that have the highest J factor, they're also the one that are really close by. So really what we're saying is this 1/d square is really important, and actually the best one are the closest one. And then in terms of specific of the results, you have all the choices that people have made in their analysis. In terms, for example, in the work we did in blue here, we have very large error bars for the ultra faint dwarf because we left a lot of free parameters because we wanted to see what the data was able to tell us without putting too much prior coming from, say, cosmological simulation. So all I want you to take home here is that the design of your analysis does matter at the end. But nonetheless, roughly, the agreement is not so bad, really, between authors. So I have this dwarf that is located somewhere in the galactic halo, but if you recall my little cartoon earlier, I'm also going through the galactic halo. So here I have the J factor for a given integration angle, quite small. You have the result of all the dwarfs with the error bars, and you have the contribution of the galaxy, of the smooth plus substructure from the galactic halo, and they're all sitting nicely above. But now if I go a bit more extremely to a larger integration angle, everyone goes up because I'm integrating the signal to higher distances. But also interestingly, now you have for most of the dwarfs, the level of the galactic contribution is roughly the same of the dwarfs. So for large integration angle, in your analysis, if you were to do this, you would have to account for the contribution of the line of sight. Okay, I need to move a bit quicker, I think so. I just want to say a quick word about triaxiality, because those objects, you remember, are triaxial, they're not spherical. And there is a way to see the effect of this if you change slightly a Zhao profile with this shape parameter, but you use at the radius something that depends on the axis of your triaxial halo. And here in this figure, what we did is taking this and integrating the J factor, orientating the halo in the 3 direction on the short, medium, and long axis. And you can see that for a core or cusp, doesn't matter. Actually, the J factor are quite similar. So that's good news in principle. We are not too sensitive to the triaxiality. Where things become a bit trickier is that this was dark matter only. I was not doing a Jeans analysis. But when you do your Jeans analysis, you're actually using projected velocity dispersion along the line of sight. And here, if you have, this is on MOG data, where we had triaxial dwarf spheroidal galaxies. If you project them along the long or short axis, it's going to give you drastically different velocity dispersion, which means that when you're going to go to your fit of the density profile and the J factor, you will be biasing your results. So while it's not critical when I'm just looking at integrating J factor here to the genes analysis and projection effect, this is something important. And there are ways using axisymmetric genes analysis. I'm trying to move away from this to mitigate this problem. Finally, my dwarf swirl is there. In principle, it has its own population of subhalo within it. Should I be interested in the boost, or should I consider substructure in these analyses? Well, not really, because I showed you this figure before, boost as a function of halo mass, host halo mass. The dwarfs regime is somewhere here, and if you look at typical boost value, you're going to get a factor of a few, or 2, or so. It's really not worth dwelling too much on substructure when you're working with dwarf galaxies. Okay, so summary for dwarf galaxies. They're a great place to look at because they're free of background. And we have, thanks to the genes analysis and other methods, it's not, here I've shown you sort of the vanilla genes analysis. There's a way to do things a bit more complicated, but because we have stellar kinematics data, we're really able to use that data to recover the property of the profiles without assuming, say, a mass concentration relation and so on. However, you need to be careful about the possible biases that triaxiality and other, I've swept a lot of things under the rug here, the biases that will be introduced by your analysis. And so checking a given analysis on mock data is always a good idea. And you're not going to be able, so this is not going to be covered in the Clumpy tutorial later on, but we have a genes analysis module in Clumpy for you to do your own dwarf swirl genes analysis if you want. Okay, are there any questions regarding the dwarfs? Breathing a little bit here. No, so again, use the chat or write that down. I'll be at the Gather Town later today. So if you have questions you're not asking now, we can cover them later. Okay, so the next bit concerns the dark galactic clumps. So this time I'm in the galactic halo, have my substructure all over the place. These subhalos are not massive enough, they did not form a star, so I don't know where they are. But some of them might be really close to us. So if in my gamma ray data, I see in a location a gamma ray source that has no counterpart at any other wavelengths, maybe have a signature that I'm seeing dark matter annihilation in this particular region. So this is why this is interesting. If you don't have detection, you can still place limits, but you need a model of the subhalo population. So conversely to what we've seen with the galactic halo, with the dwarf, where we have external data set we can use to help us infer the dark matter density profile, here we need to rely on the result of numerical simulations. So you recall all the ingredients we need to characterize the substructure population in a halo. And here we're going to be focusing on the galactic halo. And really, for all these choices, if you look at the literature and even the numerical simulation, you will have a lot of options. And it's important to sort of explore this to be able to bracket the modeling uncertainty of your result. So I'm not going to enter at all into the details, but in this analysis that Moritz led a few years back, we explored something like 8 configurations for the 7 ingredients we need in estimating the substructure component, the substructure contribution to the J factor. And we varied those ingredients one by one to see what were the effects step by step of all these choices. So one thing that is very specific to subhalos is the fact that the concentration can be radial dependent. So the mass concentration relation I showed you before was basically this dashed line here. And on field halos, this holds whatever. But if you're looking at substructure in a host halo, and this is work by Angie Molyneux a few years back as well, if you look at their concentration as a function of the mass, with increasing distance from the halo center, the host halo center, you see that for a given mass, a halo that's going to be closer to the galactic center is more concentrated than one that's located further away. So it means in my expression above that my concentration depends on the radius, and so this makes this integration more complicated because you cannot separate it, the different integral. So the reason for this is that halos are submitted to tidal stripping when they go to the inner galaxy, and you have like strong density gradients in the inner galaxy. Another thing is that really related to this is also that you may have tidal disruption of your substructure in the galactic halo when you move towards the galactic center. Here's the number of subhalo as a function of the distance in the Milky Way-like halo. And this curve here, dotted dash, corresponds to the case where the subhalo population, my dPdV, the distribution as a function of radius, would follow that of the total distribution. So it would mean that the smooth would follow the average distribution of substructure and the total. But actually, when you look at the result from numerical simulation, there are far less halos in the inner region compared to what you would expect with this very naive approach where you say, okay, I'm just going to scale down things, but overall, the overall distribution of substructure or the smooth should be the same. And that's not what you're seeing here. So this effect is naturally captured in simulations. So that when you go back here, we varied all this quantity, inner profile of the substructure, slope of the mass distribution, scatter of the mass concentration relation, and so on. At the end of the day, I'm here looking at the source count distribution, number of halo with a J factor larger than a given level. In blue and red have the result for sort of the pessimistic and optimistic models. And you can see here that I have an order of magnitude change between the two. The bottom panel, we're not going to go into the detail. This is looking one by one at all those models. So this is just by changing a little bit the ingredient you're putting, and they're all coming from the output of numerical simulation, you have a modeling error, uncertainty of one order of magnitude. Now things get even worse. You remember this plot I just showed you, and this is only with the host halo overall dark matter potential. But we know there is a disk in the inner galaxy. We have stars, we have gas, and this is an extra source for the gravitational potential. And this will yield to even further destruction of substructure. So in blue here, you have, so this is a slightly different representation. You have what corresponds to the result of those numerical simulation here in color, dark matter only. If you had a baryonic disk, and this was done either semi-analytically or using a numerical simulation, you are completely disrupting the subhalo within the inner galaxy. And this has drastic effect because now, if I use those spatial mass distribution for subhalos to do a realization of the sky, if I use the result from dark matter only simulation with no disk, this is the sort of subhalos J factor you would see in the sky. Well, see or not see, but at least that's potentially there. Now, if you use a situation where halos have been really disrupted because of the baryonic disk, things look far less promising. And in particular, for the brightest subhalo you expect to see statistically, if you have strong disruption, you're losing a factor 2 or to 10 in terms of J factor. So really, to make accurate description, prediction using dark halos, we need to understand better the potential disruption of substructure in the inner galaxy. Okay, so summary regarding that part. So they could be targets, those dark halos, though it's target we're not pointing to. So it's more in a survey mode that you hope to see something. But modeling the subhalo population for just a smooth, when I was talking about galactic center, dwarf spheroidal galaxy, I just had a simple parameterization for the dark matter. Here you start to need to have a lot of ingredients, and this brings a lot of assumption to the modeling. So you should always explore how the stability or the dependence on your result with those modeling choices. And really tidal stripping seems to be a very important point to pinpoint if we are to place robust constraint using those targets. All right, so I think I have something like 15 minutes left. So we're going to move away from the Milky Way and go to extragalactic scale. So you remember I mentioned that galaxy clusters are potentially the most, well, not potentially, they are the densest place in the universe. So it's potentially interesting to look at those in terms of indirect detection. So they are very massive. In terms of content, they have about 80%, 85% dark matter. They contain a lot of hot gas, and in terms of mass, the galaxies and the star only make up for a few percent. On the right, you have an image of the Coma cluster, which is 100 megaparsecs from Earth, at optical wavelength, seen with the Planck satellite or seen in X-rays. And the thing is that these are all different ways we have to trace the mass in those systems. So this is very interesting. In X-ray, what you're seeing is the hot gas emission from the free emission from the intra-cluster electrons. At millimeter wavelengths with Planck, what you're seeing is that when a CMB photon crosses a galaxy cluster, it is upscattered by interacting with the hot gas, and it is distorting the CMB spectrum in that location. And this is what we call the SZ effect. And this is something that can be measured. And at visible wavelengths, you're seeing the galaxies. And in terms of gamma ray background, there is an expected emission that should come from interaction from the gas and cosmic rays. But to date, I don't think there is any definite measurement that has been measured. So how do we get to the profile or the mass of those clusters? So we have various ways. I'm going to do this really quickly, depending on the wavelengths you're looking at. So at visible wavelengths, you can do the exact analogous that I mentioned for the dwarf spheroidal galaxies, except that this time the tracer of the dark matter potential are not the stars in the galaxy, they are the galaxies in the cluster. So here, as we did for the dwarf, we have a velocity dispersion as the function of the distance, a velocity dispersion profile, and you can come and adjust this with a dark matter model of various slopes. Again, this is Coma, I've just focused on Coma here. With alpha equal 1 here would be your NFW and so on. So to do this, the only caveat or a little complication is that in the dwarf galaxies, the total mass was simply the mass of dark matter. So on the right, I was simply integrating the dark matter profile up to a given radius, and that was it. Here, because the mass content in gas, in baryons, in gas and mass in stars is not negligible, you need to have some model for those as well. So this is a little bit of a complication, but in terms of the idea is exactly the same as before. Still at visible wavelengths, you could also use weak lensing to try to recover the mass of your object. So your cluster is going to act as a gravitational lens. What this will do is that it will distort the image of background galaxies. So if you have a galaxy survey, you can measure the shapes of those galaxies, and in the presence of the lens, those shapes are distorted. This is a statistical measure, and basically the amount of distortion depends on the projected mass density of the lens. So here, what is great is that you're not making any assumption on the dynamical state of your system. You're directly sensitive to the total mass. For the genes analysis, I was saying the system is in dynamical equilibrium, no rotation. There were loads of assumptions. Here, you don't need to do anything. You get directly to the total mass. You can also do some mass mapping. And again, this is a mass mapping of coma that was done a few years ago. But just to say this exists. Now, if I look at baryonic proxies for the mass, I have X-rays, I have SZ. With X-rays and with X-ray spectroscopy, you can get the gas density and the temperature, whereas SZ will probe directly the pressure of the gas. And if you assume this is an ideal gas, this is the product of density time temperature. So what people working with baryonic proxies do, they assume the hydrostatic equilibrium, which means that the pressure of the gas is counterbalancing the effect of gravity, and gravity basically is counterbalance the effect of gravity, and like this, you're able to reconstruct a so-called hydrostatic equilibrium mass by this hydrostatic equilibrium equation. So this is very well, and the great thing is that we have large catalog of X-rays, we have loads of observation, and this is very interesting, but this assumption is a very strong one, and if it does not hold, it means you may be biasing your mass reconstruction. But in principle, we have all these ways to deal with the mass of galaxy clusters. And another thing is that at the cluster scale, what we find is NFW profile are really generally a good fit to the data. So there's less ambiguity. There's never discussion of cores in galaxy cluster. So people safely use NFW profiles. So what you do generally, you go to the literature. You're going to try to find either some direct estimate of ρS and RS, but otherwise, you may simplify, find the given mass of a cluster, say the mass M500 critical. And this is typically what X-ray observation will give you. If you have an X-ray catalog, and this is what we used here for this analysis, you have M500. So actually, to go back to normalize your profile, I need a mass, I need a concentration. So you need to use a mass concentration relation. But here, big warning, you need to be careful with the mass definition. You cannot simply use a mass definition the mass concentration relation that was defined at M200 and apply it to M500. So big word of caution here, you need to do some conversion and there's some care to be done here. But anyway, again, always the same plot, astrophysical J factor as a function of the angle from the galactic center, our own galaxy. Here you have a few of the classical dwarf we've discussed before for comparison. And the point without error bars are the one from galaxy clusters. So for this work, we had a catalog of close by cluster. I think there was 2,000 of them. Here it's only the 10 with the most promising J factor. And you can see that we are roughly at the level of the J factor of the dwarfs. Okay. What about the boost? So one of the reasons that clusters were earlier on invoked as great targets for indirect detection is because at the time, if you look at papers in the 2010s, early 2010s, boosts of factor 10 up to 1,000 were claimed. And of course, if you have such large boosts, these objects become really promising. But what those earlier studies did was using a mass concentration relation obtained from numerical simulation, as you do, it's absolutely fine. But the mass resolution in the simulation is only limited to the high mass range at that time. And so they were just using an extrapolation, a power law extrapolation of the mass concentration relation. So they were basically predicting much more concentrated low mass halos than we know are now. And with such high concentration, it means that the single halo luminosity is much higher, and so the boost was really large. Nowadays, these boosts are excluded, and if you look again at this figure that you know by heart now, the boost as a function of the mass, in the cluster regime, we expect boost of 10 up to 50 maybe, but definitely not 1,000. So this is what was included to do the figure on the left. Of course, if I was to multiply this by 2 orders of magnitude, those points, these would become very, very interesting targets, but unfortunately, this is not the case. So in terms of galaxy cluster, they are the densest part of the universe. We have a large catalog of close-by cluster. You can, something I haven't mentioned, you have also the option to go and stack the signal of the cluster when you have such a large survey, so this could be interesting. Their masses profile can be determined using multi-wavelengths information, visible X-ray SZ, and one of the good things is that maybe you can cross-check the results because they all come with their limitation. But generally, Cuspy profile and an FW profile are fine when dealing with galaxy cluster. You have some substructure boost, but typically the J factor you find, despite of those boosts, are of the order of the dwarfs, nothing more. And you do expect some background in those objects. So all in all, there may be a bit more complicated places to look at. It doesn't mean we should not look at them, definitely, because we need to look at everything. But just from the J factor perspective, they may not be the best place to look at. Okay, so I'm nearly done. So I would like to ask if there are any questions here regarding the clusters. Okay, so hopefully everything's clear. The last thing that I hadn't listed in my list of targets is the diffuse exotic signal from the extragalactic. In the sense that it's not a target, it's not something you can point out, but in principle, the dark matter distribution in the entire universe will contribute if dark matter annihilates anywhere. I'm going to have a gamma ray signal. It will propagate towards us, and in any direction, I should have a sort of a constant level for this diffuse exotic signal. So very briefly, at the galactic scale, we were able to split the expression of the expected flux by a particle physics term and an astrophysical J factor. So the question I have here, and the way I'm framing it, maybe the answer is obvious. Can I still do this when I'm thinking of integrating the signal over large extragalactic distance? And why? And what new ingredient would I need to address this question? So first of all, I am again going to ask for a quick show of hands. Who believe that this should be written differently? I think I lost everyone at this stage. So can I still separate particle physics and J factor? So I have Lorenzo who thinks we should write this differently. Anyone else? Loretta as well. So what's happening basically if I integrate, okay, more Chauvins, excellent. So if I go to extragalactic distance and start integrating things over cosmological distances, what's happening to the spectrum? Well, it will be redshifted, right? So far, we've only been considering the close-by universe. So there was no redshift, all my distances, everything was behaving nicely. But the moment you want to go at extragalactic scale, you need to put the spectrum, the integration become an integration over the redshift range, and the spectrum is going to depend on your redshift. So we cannot split this into two terms. So there is no equivalent, there's no J factor for the extragalactic. When you deal with the extragalactic, you have to take the entire expression. So we're working directly with the flux. So in terms of new ingredients we're going to need cosmology. We're going to need the halo mass function. You remember, so it was nearly 2 hours ago now. very beginning of the lecture, I told you about the expected number density of halos in the universe as a function of mass and redshift. So we're going to need this. And if you recall the lecture from Alberto Dominguez on the extragalactic background light, we're also going to need this because the EBL is going to absorb some of the gamma rays. So we're not going to do the demonstration together. I'm just going to pop up the expression here and go through the terms. So this time, I'm integrating. So this is the intensity. I'm not integrating over the solid angle here. I've put it at the denominator here. So my integration along the line of sight become an integration over the redshift. The source spectrum is here now. And if I'm observing photons with an energy E gamma, it means they have been emitted at an energy E gamma times 1 plus Z to account for the redshift. And this source spectrum is absorbed by the EBL. Those energetic gamma ray photon will interact with the photon from the extragalactic background light to produce pair production, electron-positron pairs, and they're going to be absorbed this way. So this is the spectral part. And then I have this so-called intensity multiplier that comes from the structure formation. And this one hurts a little bit. This is the integration over the halo mass function, number density of halos of the function of mass and redshift, time. This one we know, this is the only thing we know from before, is the single halo luminosity. So I have a halo at a given epoch, at a given redshift. I have its mass. I have a mass concentration relation for that redshift. So I have the concentration of that redshift. So I'm able to compute its intrinsic luminosity. Everything is point-like in this picture, okay? So this gives you the intensity multiplier. The halo mass function is written like this below and involves the sigma, which is the variance of the density field at the scale defined by the mass. So if you remember, I have m delta. This gives me a r delta from my mass radius definition. So the variance of the density field is integrating the linear matter power spectrum, so this comes directly from the cosmology, over a window function that is a function of the scale I'm looking at. The scale depends on the mass. Once I have this, I can plug this into the halo mass function. Numerical simulation or Press-Chester or whatever give you this function f of sigma z. This is called the multiplicity function. And when I have my halo mass function, I can plug that into delta square. And then you have other factors here coming from cosmological distances and so on. So these are just coming from this. And you recognize the term that we can put out of the integral, the sigma v and the mass of your candidate. So this is how you express this. And very briefly, again, all of this, if you go to the literature, there's various parameterization for the halo mass function. There's various parameterization for the EBL absorption. You can choose different things for your halo profiles. So we can explore all this. This is something, again, that Moritz led, a study he led a few years back, where for all these ingredients, you're going to vary with typical things you find in the literature to be able to then place a sort of modeling uncertainty band over your result. So here, this is a predicted flux as a function of energy from this extragalactic signal. And I don't have time to go through the detail, but I just want you to look at this green band here, which basically comes from the fact that we've been varying the ingredient in reasonable range, but still we have something like an order of magnitude uncertainty at the end. Okay, so I am done. I'm just going to very briefly conclude that to do anything with dark matter indirect detection, of course, you need to take care of your data analysis and astrophysical background and so on, but you also need a robust estimation of your J and D factor. And by robust, I mean either so of course, best estimation possible, but also error bars on this you are sure of and comfortable with. Numerical simulation provide a lot of insight on how to model the dark matter distribution. So we've relied a lot on dark matter only simulation. Now we have hydro simulation giving us new information. And basically what we did here is take those results and parameterize this in some way. Everything has a parameterized form based on what the numerical simulation tells us. So for the dark clumps, we can only rely on the numerical simulation. However, for any other target, galactic center, dwarf total galaxy, galaxy clusters, we have information from observation at other wavelengths. Sometimes even from people who don't really work, I mean, they're not particularly interested in dark matter indirect detection, but there is information there that help us constrain the dark matter profile. But doing so, we are making a lot of choices that might impact the result. So it's important to remember to check the dependence on your result, on the reasonable range for all your ingredients you put in it. And finally, as of last week, the last version of Clumpy is out, thanks to the great efforts of Moritz. And so for this afternoon hands-on, if you haven't installed it yet, you should directly go install version 3.1. And if you want to update for the hands-on, you can, although you don't really need that specific version for the hands-on. So I will stop here and I thank you. And if you have any question, please tell me.
Thank you so much, Celine. Thank you for this nice comprehensive overview. I think it was really perfect for the purpose of the school. Okay, so it's a bit late, but let's take a couple quick questions, if any. If not, we can always go to Gather Town, but let's see if we have any questions now. Okay, so it seems people are hungry already, Celine.
Yeah, I had lunch before because like 2 p.m. for me is crazy.
Yeah, but you know, this is Spain, so it's
I know.
fully Spanish schedule, you know, here.
I know. So, okay, so in any way, we'll be at Gazetan and we have the hands-on this afternoon and I'll be there with helping out with Moritz. So
very good. Okay, great. Indeed, I think we already sent you guys an email about that, but we're going to have the full hands-on session this afternoon on Gather Down. Okay.
Okay.
So yeah, I already agreed with Maurice about this change.
Okay.
I think it's going to be fun, and we had a very nice experience last Friday with the machine learning hands-on session. So I think we can repeat it there.
Okay, great.
Yeah, so let's I think we can already meet directly in Gather Town at 3:30. In any case, we'll be also in Zoom just in case there is someone lost around, you know, and we will basically be taking him or her to Gather Town too. Okay, so yes, time for lunch or for whatever you want to do for a break until 3:30. Okay.
Thank you. See you
Thank
later.
you, Celine. Thank you.
Bye.
Bye bye.